So we already talked a little bit about relationships and graphing them in section 4.1, and now we're talking in section 4.2 about patterns and linear functions. That means we're going to identify, represent patterns that describe specifically linear functions, not just any kind of graph. And first of all, a relationship between two variables, we always have the dependent variable that will change in response to the variable that we call the independent variable. So again, you want to think which variable causes the change in the other one. So independent variable causes a change in the dependent variable. So values of the independent variable, we call those inputs, so that's what you were starting with. And then values of the dependent variable, so after you've made your change, that's the outputs. Value of one variable may be uniquely determined by the value of another variable. Such relationships can be represented using few things, such as tables, words, equations, sets of ordered pairs, and graphs. And some questions might be asking you to do more than one of those. So in this first question, for example, diagram below, what's the relationship between the number of triangles and the perimeter of the figure they form? Got to represent that a few ways. Represent that relationship using a table, using words, using an equation, and using a graph. So starting with that first part, a table. So a table just means we're summarizing that information. So if I have one triangle, two triangles, three triangles, four triangles, I list that down my table for, looks like it's cut off here, but should say number of triangles. So number of triangles, 1, 2, 3, 4. And if we count out the perimeter for each figure, first triangle has a perimeter of 10. If I add another triangle, count out that perimeter, I get 14. Next perimeter is 18, and the last one is 22. So we describe that using a table just by listing what we see in terms of triangles and perimeter. If we want to describe that relationship in words, we can make a connection between the triangles and the perimeter. So it looks like every time I add a triangle in my figure, my perimeter is going to increase by 4. So the other sides are covered up, but that one side that's added adds 4 to that perimeter for the figure. If I want to use an equation, I could represent that. I use two variables, p and t. So p you could also identify is what we're using to call for the perimeter variable. And t, that's going to be your triangles variable. So the perimeter is going to be 4 times however many triangles you have, and then another 6. So again, if I look at that first triangle, it's not just 4. I have an extra 6 to get me to 10. And you could also describe that in words as well. Last part, now that I have my equation, or if I have some of my triangles from the table, I can put that information into a graph as well. So again, dependent variable, we want to choose as the perimeter because it depends on the number of triangles that we have in our figure. So independent variable is triangles, dependent is perimeter. So if I have one triangle, that was 10, two triangles was 14, 3 was 18, and 4 was 22. So fit those into our graph, we can kind of see what kind of pattern that forms. So if I want to know the perimeter of n triangles, so just anything in general, if I know the perimeter of n triangles, we could find the perimeter of n plus 1, so that next figure in the sequence, if I just add 4 to the previous perimeter. So again, if I started with 3, I knew the perimeter of 3 triangles is 18. Even if I didn't have the table, like for example, we could get, if I wanted to fill in 5 triangles, I could just continue that pattern, just take the previous one and add 4. So I'd end up with 26. We didn't have that in our figure, but we could guess based on the pattern. And last question, how does your answer in 1b relate to the equation we wrote in 1a? And again, the equation we wrote was here, 4t plus 6. So 4t in that equation represents an increase of 4 for every triangle that you add. So if I increase t by 1, that means if I multiply by 4, I'm really increasing the perimeter by 4, not by 1. So if I take that a step further, we have a few other things we could describe. We could describe the relationship in the last problem by saying the perimeter is a function of the number of triangles. And that function word's important. We're going to be using functions and specific naming a lot. So a function is a relationship that pairs each input value with exactly one output value. So again, you want to think in terms of what you start with and what you finish with. So sometimes you can see it's kind of like a function machine. Think of it as feeding in inputs. Your function is going to do something to that input, and it's going to result in exactly one output. So you can never have more than one. You've seen that one way to represent a function is with a graph, and a linear function, specific example again, is a function whose graph is a non-vertical line or part of a non-vertical line. So definition is kind of in the word itself. You kind of see the word line there in linear. So if it's a linear function, that means it's going to form a line. So the relationship in this table, if we have to decide if that's a linear function, we're going to also describe that relationship using, again, a few different answers, words, equation, and a graph. If I'm trying to put that together, it looks like from my table, every time I increase the input by 1, the output's going to increase by 2. So we can kind of describe that relationship. But also if you want to put that in terms of an equation, I can't just say it's 2 times whatever the output is. It's 2 times the input, first of all. So it increases by 2 every time I increase the input. But we also have to add 8 because if I start with nothing, I still have 8 for the output. So we start at 8 and then add 2 every time you increase that input. On my graph, I can just take those points from the table, fill them in on my chart. So I have x's going horizontally and y's going vertically. 0 and 8 for the y. 1 was 10, 2 was 12, and 3 was 14. And I kind of made a little faint line there. So we would just have those 4 points. It doesn't really describe any equation. But if I see that they would form, as much as I can draw a straight line there, it would draw a straight line between those points. So if I see that it's going to form a straight line, if I connect all of those dots together, I can say that yes, that relationship would be a linear function because it does form a line. So also I can just do that if I'm given some ordered pairs. So this time I don't have a table for it, but I do have some values. And if I look at that set, 0, 2, 1, 4, 3, 5, 1, 8, if I want to see if that's a linear function, you could put it in a graph. So if I graph out what those points look like, it would look something like this. And if I'm trying to explain if that's a linear function, first of all, it's not linear because this doesn't look like it's forming any kind of line that we can use. But it's also not even a function because remember, for a function, the input value, so that first value we see for the x's, can never have more than one output value. So for 1 right here, 1, 4, and 1, 8, since I use 2 different outputs for the same input, that's not a function, not even a linear function. Yeah, it's not a function in general. So we've looked a little bit about linear functions. 4.3 is about expanding that to also look at nonlinear functions. So still looking at patterns, but now we're expanding that to nonlinear patterns, nonlinear functions. The relationship in that example, we might work on this together as a class. That's an example of something that we see as a nonlinear function. So a nonlinear function is a function whose graph is not a line or part of a line. So if it's linear, it's a line. Nonlinear, not a line. Kind of get those definitions just from the word itself. So just like linear functions, we can answer nonlinear functions in a few different ways. We can answer them using words, tables, equations, ordered pairs, and graphs again. So a lot of those same ways we use to describe linear functions also applies to nonlinear. And if I want to see the difference between those, again, a linear function is going to be a function whose graph is a non-vertical line or part of a non-vertical line. So if I have a line, or if even it's just a bunch of dots, that's also part of a line. So these all count as linear functions. And nonlinear functions, again, just means the opposite. It's a function whose graph is not a line or not a part of a line. So if I have what's called a parabola here, that's not a line. This would be a cubic function, that's not a line. And also, it looks like 2 lines put together, but still doesn't count because it all doesn't form one line. So those are all examples of pretty common nonlinear functions. And if I look at that first example, try and tell what kind of graph that is. A table below shows the fraction A of the original area of a piece of paper that remains after the paper has been cut in half n times. So basically what this question is saying, I start with a piece of paper, cut it in half, keep cutting it in half over and over again, and I can see what kind of paper I'm going to have left after those cuts. So if I want to graph that function represented by the table, we're also going to have to decide if that graph is linear or nonlinear. And first thing you want to start with when you're graphing this, you got to be really careful about your spacing. If I'm making my graph, it's easy enough for the number of cuts, 1, 2, 3, and 4. So again, since that's the independent variable, we're going to put the area remaining on the vertical axis because that depends on how many cuts you're making. So you want to be really careful. I made my scale go by 1/16. So 1/16, 2/16 would be 1/8. Then we have 3, 4/16 is 2/8. So you can also think in terms of eighths. Skip 1 3/8 and 4/8. Again, 4/8 is the same as 1/2. So that's as high as we need to go. So if I want to make my original area, all I have to do is take my points and plot them in. So 1 cut, I have half my paper left, same as 4/8. If I have 2 cuts, that was 1/4, so 1/4 is the same as 2/8. 3 cuts was 1/8, and then 4 cuts was half of that. That was 1/16. So I can see just based on my graph, it doesn't look like it's forming a straight line. And this is where you want to be careful about your graph. If you have graphing paper, this is easier to see because you might have different spacing like I have, a little bit of different spacing here. But either way, it doesn't look like that's going to form a straight line. So function is nonlinear, so it doesn't decrease by the same amount each time. That's not going to form a straight line. So you can also think in terms of this word problem, would the area ever reach 0? So the area would not reach 0 if you keep cutting a piece of paper in half. There's no way they're going to end up with no paper left. You're always going to have something left to cut. So this answers something like that. You must be left with some paper. If I'm cutting paper, there's always going to be that extra half that we didn't cut yet. So I can never reach 0, but I will be closer and closer to 0 as those pieces get smaller and smaller. Trying that again with our second question. Table shows the number of new branches in the figure using the pattern below. And just like the other questions, we have to find the pattern, first of all, to complete our table, and then represent that relationship using words, an equation, and a graph. So answering 3 different ways. So first of all, if we're answering in words, we can fill in the table first. It looks like every time I increase my x, so if I take the next figure, it looks like my branches multiply by 3. So times 3, times 3, times 3, times 3. And if you want to think of the connection instead of the connection just between the y's, if I want to think of how I go from x to y, I basically just take 3 and raise it to the power of x. So 3 to the first is 3, 3 squared is 9, 3 to the third, 3 to the fourth, 3 to the fifth. So I can describe that, again, as a power. Number of new branches is 3 raised to the power of the number of the figure that you have. So whatever I want for the y's, I take 3, raise it to the power of the x. So that's my equation. Y is going to be 3 raised to that figure number. And if I want to put that in terms of a graph, I kind of ran out of space here, but I can put those points in. So 1 for x, 3 for y, 2 for x, 9 for y, 3, 27, 4, 81 is already pretty far up there. So when I went to 5, I just kind of didn't even include that point. But already we can tell that this is not going to be a linear function. That is another example of a nonlinear function. So a function that can be thought of as a rule that you apply to the input in order to get the output. So remember that kind of function machine. You're doing something to the function to adjust that input to get the output. And we can represent a nonlinear function with words or with an equation, just as what we did with linear functions. So our last rule there, if I'm just trying to describe how do I get from my ordered pairs, again, how do I start with the x for the input, end up with a y for the output? So if I start with 1, how do I end up with 1? If I start with 2, how do I get 4? If I start with 3, how do I get 9? And the pattern that works for all of those is if I just take my input, if I just take my x, if I square that, I get the y value. So 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So whatever I start with for the x, my function is to square that, and that's going to be my rule. So y is going to be whatever the input was, I square that. That would be my output. So make sure you have these completed, and we'll work on that practice together in class.